How's it going? It's my first time in Vienna, so thanks for having me here. Yeah, well, today I'm going to be talking about how to circumvent deep learning systems. In specific, I'll be looking at classifiers that are implemented with deep learning. But actually, we can see that using some of the techniques that I'm going to be talking about today, you can bypass a lot of other machine learning systems that are not just implemented with deep neural networks or artificial neural networks. So a little bit about myself. I live in San Francisco now. I work with a security company called Shape Security. This is independent research that I did on my own time. And I did my bachelor's and master's at Stanford doing AI as well. So just a little bit of background on deep neural networks. I won't be going into a lot of the detail here because a lot of it you can find out online and you can go into the theory and math behind it yourself. But I'll just be going into some of the high-level details around it because I feel like it's a little bit necessary for understanding some of the concepts in this talk. So this is a diagram of a three-layer neural network. It's a very simplistic feed-forward neural network where you have three layers. And so when people talk about deep neural networks, this isn't what we consider to be deep. There's only three layers. This will be what you consider more to be a multi-layer perceptron. The first layer is the input layer where you take in input, an input vector, for example, and then each unit in the input layer is connected to every other unit in the middle layer, which we call the hidden layer because you don't get direct access to it as a user of the neural network. And then basically when each input unit is fed through a unit in the input layer, it will be sent through an activation function, which we call f here, and then it'll be multiplied by a weight w. And you can add bias units to it, which basically act as a way for you to shift the value around. And then eventually the same thing happens between the hidden layer and the output layer, and then you eventually end up with a bunch of prediction vectors in what we call the logits, which we feed through a normalization softmax function to get a prediction. So in this particular case, we see the predictions to be 0.34, 0.57, and 0.09. The output layer simply tells you which predicted class it is in the case of a classifier. This is a simple multi-class classifier. So the predicted class in this output vector is actually position 1, whereas the correct class is position 0. So we see that the neural network made a wrong prediction in this case. So how do we train neural networks in the case of making wrong decisions? The first step is what I just talked about. Each unit receives the output of the neurons in the previous unit plus a bias signal, and then it computes a weighted average of the inputs. It applies some weighted average through a nonlinear activation function, of which there are many rectified linear units or sigmoid functions are more popular ones. And then you send the final layer through the softmax function. So in the case there is a wrong prediction, that's what we call training of a neural network. And this training step is done in the backpropagation stage. And that in essence is what training a machine learning model is all about. When you have a reinforcement model, what you're doing is you're feeding an input through a model and then seeing if it makes the right or wrong decision. If it makes the wrong decision, then you help it to make the correct decision by penalizing the input units that contributed to making of this wrong decision. And the whole concept around neural networks is about assigning blame. So what you're trying to do is to find the input units that contributed to this wrong decision, and then you listen to it less in the future. So you decrease the weights that contributed to this wrong decision, and in the future when a similar input is fed into this neural network, and then you will find that those units will contribute less to the eventual result, and hopefully it'll give you a right output this time. A lot of this can be optimized with stochastic methods like stochastic gradient descent and other kinds of optimization algorithms that are typical in machine learning algorithms. So I'm going to be starting off with a very, very quick demo here. This is the CIFAR10 dataset, which is a typical dataset that is used for a lot of training and academic work in machine learning classifiers, in particular deep learning classifiers. You can go and play around with this. There are pre-trained models in several deep learning frameworks like TensorFlow, Keras, that make use of the CIFAR10. So what this is it's 60,000 32 by 32 pixel color images. So there's 3 channels RGB. There are 6,000 images per class, which just means that there's equal distribution of images in each of the 10 classes. And each of the 10 images so here we have chosen 2 different classes of images, the dog and the automobile. And what we're trying to do is to generate adversarial examples just to show you that something that looks like a dog to the human eye, when you actually feed it through a neural network, it can actually give you a wrong decision, even if we use a pre-trained model that gives you a 99.9% accuracy classification. So I've pre-generated some examples here. Dog_f is the adversarial example input, and dog_norm is the normal one, which we saw gave you a correct output. We compare the 2 images. The dog_f looks a bit more noisy than the dog_norm, and we run it through the evaluation function. It tells you it's a ship, which is totally wrong. So we run it through dog_f1, which is a little bit closer to the normal, and it still tells you that it's a ship. So that's really weird. And the whole point of this talk is to show you that you can generate images that look similar to the original image, but can totally trick or mislead a classifier model that is implemented with machine learning. So we see the same thing for the automobile case. In the normal image, it correctly predicts that it's a normal automobile, and in adversarial one, we see it tells you the wrong thing. Yeah, it says it's a cat, which is wrong. So this is the pre-trained model on TensorFlow. You can download the model yourself and play around with it. And I'll be releasing, I have released a framework this year at DEF CON to generate these images yourself, and to basically add on some perturbation to images that will allow you to generate arbitrary adversarial examples for any image that you choose to train on any model. So let's just go a bit into the details of what is contained inside each one of these images. We'll look at the actual pixel values to see how they differ. Just to show you that the actual difference in the pixel values is pretty small, and only a very small perturbation is required for a wrong prediction to be made. So obviously, the smaller the perturbation, the less obvious it is to the human, because if you see like a very noisy image, then it is easy for a human to guess that, oh, maybe this is an adversarial example of an image, maybe someone is trying to trick the model. We see the values of each pixels range between 0 and 255. The shape of each image is 32 by 32 pixels. There's 3 channels, so it's a 3-dimensional tensor. And so these are the raw pixel values. What we want to see is the difference between the adversarial image and the normal image. So let's look at the adversarial image's shape. And then we take the difference by simply just subtracting the matrix of the adversarial image from the normal image, or the other way around. And then we just print it out just to see how different they are. So we see that each pixel actually only differs between 2 and -2 in terms of the raw value of the pixel, which is virtually impossible for a human to tell that something is going on. So yesterday there was a very interesting talk about steganography, and this is a way to encode some kind of image, some kind of information in the image, which would help a machine learning model to misclassify an image. So you don't exactly know what is going into this image that causes the machine learning model to make this wrong prediction. And you see, like, this is the noise that we're adding to the image. It's a little bit trippy at first. Like, I couldn't imagine that adding that vector to this image would cause an image that looks so similar, but that actually is how RGB works. So let's just go on here. I'll be looking at a couple of different kinds of attacks. In general, there are different classes of attacks, and adversarial machine learning is a field that has existed for the past 5 or 6 years. It was first introduced in a paper from Berkeley in 2011, and in general, the kinds of attacks are causative and exploratory. So what this means is that if you have access to a training phase of the machine learning model, then you can actually inject some stuff into the training samples in order to help in order to make the model learn something wrong. For example, some research that I did last year involved injection of samples into the training phase of a SVM classifier, which will allow the classifier to learn something that is unexpected. And then during the testing phase, the person would not expect a classifier to think that, for example, a piece of malware is non-malicious. But since it was trained using malware in the training phase, during testing phase, this classifier would actually think that this piece of malware is benign. So the attack that we're talking about today is actually a little bit more interesting, I think. You don't actually have any access to the training phase at all. All you have to do is to look at the input and the output and have access to the sample that you're trying to perturb. And this has a lot smaller attack surface because you don't need to know anything about the model that's being used. You don't need to know anything about the type of training that's done on this machine learning model. As long as you know that there's some kind of unsupervised feature extraction, which is what deep learning is, then you can actually help to guide your processes in how you add this perturbation to any image or any kind of input. So it doesn't only work for images. Later I'll be showing an example of an online service, Gmail's malware classifier, that we can actually add some perturbation to a binary file and then cause the malware classifier in Gmail to not recognize this piece of malware as a malware while still maintaining its malicious behavior. So why can we do this? Let's take a step back and think about what machine learning models actually learn. When you think about a classifier, an image classifier that we saw earlier, for example, and you see that the machine learning model manages to classify with 99.9% accuracy that an automobile is an automobile, a cat is a cat. As humans, we think that they're learning the same things that we do, that they're looking for the same kinds of features that we do. So the ways that we recognize that a cat is a cat, for example, is that it has a furry head, it has whiskers, it has 2 ears, but that's not actually what the machine learning model sees. A lot of the time, especially, for example, if you're using convolutional neural networks, it's actually looking at different features from the pixel level down to the cluster level. It's looking at different colors that may cause it to think that a particular image belongs to a certain class. So we don't actually have a very good idea of what machine learning models are learning, and that's the whole idea of the field of explainability in machine learning models. When a prediction is being made, we want to know why a prediction was made, and we want to give an explanation so we can understand why something was classified the way that it was, especially for unsupervised learning models like this. So there are 3 very simple steps in adversarial deep learning. I won't be going to the math behind this. There are some papers published in this space by researchers in various different fields, but and I've implemented some of these methods in the deep Pwning framework that I have put on GitHub that you can play around with. But in essence, there are 3 simple steps. First step is to run the input X through the classifier model. If you don't have access to the classifier model, then you can implement a substitute model that can be arbitrarily chosen based on a good guess or based on what task you're trying to accomplish. So for example, if you're trying to have an image classifier, you would run it through a very typical convolutional neural network. If you are trying to approximate the model for an online machine learning as a service kind of classifier like Amazon ML or Clarify, then what you would do is you would choose a shallower network, since these networks are, you can guess that they'll be shallow because once they're too deep, then they tend to overfit. So a lot of this can be done with simple guessing, and even if you don't guess correctly, we still see that you still get some pretty good accuracy. Like, for example, I don't know exactly, no one knows exactly how the Gmail malware classifier is implemented, but I implemented a substitute model based on a 4-layer feed-forward neural network, and it managed to work pretty well with about 60% accuracy. So the second step is based on this model prediction. You derive some kind of tensor, some kind of vector that you can add to this input to maximize the chances of misclassification. So first of all, you traverse the manifold to find blind spots in the input space. This is the most brute force approach. It's the slowest approach, but it's also pretty reliable. The second kind of approach is a linear perturbation, and this requires you to have access to the model weights, and with the weights, you can have access to the cross-function gradient. So I won't go into the math around this too deeply again. The third method is an optimization of the second method, where basically you're only perturbing the pixels or the input units with the highest saliency. And we'll look at what saliency means later. And the third step is the simplest, which just means that you're going to add this perturbation tensor to the original image. And just by adding this perturbation tensor to the image, you have formed an adversarial example. So saliency means the amount of influence that a selected dimension or a selected unit has on the eventual output. And here we see like the 32 by 32 pixel image. Which pixel position actually affects the output the most. Let's say if you change a pixel value on the very edge of this image, we see that it's actually not going to change the output a lot, just statistically speaking, looking through the entire data set. But if you change the pixel value of the very center pixel by just a value of 1, then we see that it actually affects the output a lot more. And so we can have optimizations on adding the perturbation tensor to the original image by changing pixel values less, and this will help to avoid detection, because to a human eye, if we see like an image differs from the original image less, then we're less likely to suspect that there's some kind of foul play going on. So again, increasing attacker knowledge makes it a lot easier for an attacker to attack a machine learning model. If all you have access to is a black box, then it decreases your chances of being able to trick this model successfully. So this is common sense. If you have access to everything, like the model hyperparameters, the kind of architecture that's used, the training data used to train this model, then you can very reliably generate samples that will trick this model. So here I have another quick example. So captchas are something that is famously used to distinguish bots from humans, right? And there's a lot of online services that help you to solve captchas, basically in like a mechanical Turk kind of way. But then that's not really scalable, so there's people that use deep learning to derive models that can solve captchas, that can recognize images and then tell you what this captcha actually is without any human involvement at all. So here, I'm actually testing out a captcha solver implemented by someone else using deep learning, and then we'll see how we can change the captcha in such a way such that the captcha solver can no longer solve this. And so this is just the code used to evaluate the captcha. It's calling into the deep Pwning library, which will be released. And so first of all, we have to generate some captchas. I'm generating captchas that with just this simple PHP library, generating 10 captchas at a time. Very typical looking captchas. They look like that. In fact, some of them may be a little bit even hard to solve for humans because they're like too warped in some direction. And you see that they generate random captchas every time. It's only from A to Z. And this is just for facilitating of a faster model training time. Training deep learning models is actually pretty computationally intensive, especially if you don't own a GPU. I actually trained this on an Amazon GPU 2.2x cluster, which is a little bit expensive. I spent about, I think, $190 USD training this. So it takes some time. You can see that this is the training logs. I started training on July 12th, 5:53 a.m. And by the time it was done, it's July 13th, 9 a.m. So it's more than 24 hours here. And you see like the validation shows that the model accuracy is 98%, 98.2%, which is a pretty good accuracy for solving captchas because a lot of the time it's harder than looking at just raw images, looking at the classes of images and trying to classify a cat as a cat, for example, because the differences between the letter A and the letter Q, for example, they're a bit nuanced. So let's just evaluate this and see that it actually does solve models and gives you the correct predictions. So I'm running the evaluation function on these 10 examples that I just generated here. And you see, okay, it doesn't always perform perfectly, but now okay, it's okay. So it predicted all of the characters at each of the 6 positions correctly. Looking at one example, let's look at the first one. It's IACTGB, which is correct. And if we look at the actual captcha, okay, yeah, so IACTGB is correct. And let's look at how to generate adversarial examples for this. So IACTGB's example looks like that. And what we're going to do is to run it through an adversarial generation function. So we want to generate captchas that have some kind of perturbation tensor in there. So this deep learning model, which is the same model that we used to solve it with 100% accuracy previously, can no longer solve this well. And live model is just a function that I use to generate the adversarial examples. What it does is it feeds it through a substitute model. The substitute model is actually the same model that's used to train. Since I have his code, I have his model. It's on GitHub. And it's slowly generating the adversarial examples here. So in data select 00 add. And this is actually using the fast gradient sign method. It's a method that's devised by Ian Goodfellow at OpenAI. And so you see the differences between the images. It's actually pretty incomprehensible. You can't see any obvious differences between the images here, and that's because on a white and black image, it's harder to tell when a pixel is slightly lighter than pure black or is slightly darker than pure white. The human eye is just in general bad at telling differences like that. So for black and white captchas, it's really not obvious when you're dealing with an adversarial sample. So humans can obviously still read it correctly. And what we want to try to do is to make these auto captcha solvers not work. So let's test it on an adversarial sample. And I'm going to fast forward a little bit here just to show that it's going to solve it wrongly. So give me a sec. Generating the examples. And we're going to generate all the 10 examples. We're just going to test, we're going to run it through the same evaluation function here. Okay, so let's run it through captcha model eval. And we'll take in the input of this folder, and then we'll see what kind of predictions it makes.
Can you maybe zoom in on the camera a little bit? Because you see a lot back there.
Yeah, give me a sec. So, okay. Let me see how to zoom in here. I can't really zoom into this now, but the point here is that I just want to show the precision values. And so the precision previously was 1.0 at all the character positions, and now the precision is 0.1, 0.2, 0.4, 0.7, and 0.3, and 0.3. So it means that out of the 10 examples, if it's 0.1, only one example was solved correctly. And if it's 0.7, then 7 out of the 10 examples will solve correctly. But to solve a captcha, you have to have all 6 characters solved correctly for each example. So this is an example of how adding adversarial examples adding adversarial perturbations to an input image will cause a deep learning model to not be able to recognize stuff correctly. And so the slides will be online and everything, so if anything is like too small or unclear, then I'll post them online later. I mean, so you can look at it yourself. So the whole idea behind not having to know a model beforehand or not having to know the exact way that a model was implemented, that's not really clear why it happens, and it's still an active area of research. But the thing is that adversarial samples that fooled a model A have a good chance of fooling another previously unseen model B, even if you don't know how model B is implemented. For example, model A could be a linear classifier, and model B could be a clustering algorithm, a clustering classifier. And we see that if you generate adversarial examples using a deep neural network, you can reliably generate samples that will trick any one of these models. And there's a graph here of the chances of being able to trick models based on the source method that you use to generate these samples and the target model that you're trying to trick. And using substitute models is a good way of generating samples like this. All you have to do is to train a new model based on the input and the output of the target classifier that you're trying to trick. And then if you have access to the actual output vector, then that's great. But if you don't, then it's also okay. So what I mean by the target model's output vector is that you have the prediction probabilities of each of the classes, which isn't always the case. An example would be something like a digit classifier here, where you have, let's say I have the digit 0, and it gives you the probability output vector here. So the probability that this is a 0 is actually 0.56. And so because this is the largest value in the output vector, it actually predicts it as a 0. If I have a 2 here, then it predicts with probability 1 that it's a 2. So what I mean by having access to the entire output vector is when you have this entire vector and not just the result 2. And that helps you train a model a lot better and helps you train a substitute model a lot faster because you have access to a lot more training points, and helps you gain convergence much faster. And so now we'll look at the malware misclassification problem, which is basically what I explained earlier. What we're trying to do is to make a unknown machine learning malware classifier think that a malicious piece of software is non-malicious when it actually still retains its malicious behavior. And so the training set we're using here is from the Contagio data set. It's a very popular malware classification data set. I'm only looking at the portable executable samples. I'm using about 1,500 malicious PE samples. And the PE extraction feature list is not really the focus of this work. I took it from a paper written in 2012 about the best features to select from portable executable files for malware classification. And a lot of the features here actually don't deal at all with the actual code analysis path of the executable. There's some research done previously where they found that a malware classifier written with machine learning that was used to detect PDF malware can actually be tricked just by adding stuff to the header section of the PDF. So it doesn't actually deal with any of the raw contents of the PDF file. Just adding some padding to the header file could cause the classifier to think that it's not malicious, even though the code that's being executed is still exactly the same. So what we're doing here is similar. We're not dealing with the code path at all. So obviously this doesn't work for malware classifiers that do any kind of static analysis or program binary flow analysis. But a lot of malware classifiers actually don't do that because it's pretty complex, and I don't know of any machine learning malware classifiers in existence that actually do something like that. There may be. And this is this is the architecture that I have that's used to generate the malware samples. From the left to right in the middle here, what we see is the way that we train the model. We have benign samples and malicious samples. These are two classes, so it's a two-class classification problem. Then we extract the features based on the feature set that we saw earlier, and then we run it through two different classifiers, the target classifier and an oracle. And what this oracle is something that, that helps to ensure that this piece of malware does indeed contain the malicious behavior that was previously that we previously said it had. So, for example, when we change any piece of malware by adding a header file or by adding padding to the end, then what we want to do is to ensure that this piece of malware still retains its malicious behavior, and then we use this to train the deep neural network. And so in the actual testing phase, we run a malicious seed through it, which is the binary file that we want to evade the classifier. And then we run it through an iterative mutation phase. And then we see if it still retains its maliciousness. And then if it retains its maliciousness, we evaluate and see if it actually tricks the model. So you see that the Gmail malware classifier, it's really easy to test. You just drag and drop your binary into the Gmail inbox compose window, and then it will tell you if there's a virus or not. The evasion rate after evasive alteration is about 47%. See that there's a very low false positive rate. So at least for the 1,500 malicious samples that I tried, there are 0 false positives. So I think because they want to maybe optimize for user experience, they're not being overly aggressive in how they flag maliciousness in binaries. So let's look at a demo here. And what I'm talking about is Gmail, when you go into the compose window and you actually drop a piece of malware in there, a malware binary or executable, they'll actually do a scan, some kind of scan using a classifier model, and then they'll tell you if it's malicious or not, and they won't allow you to attach the attachment if there's a virus detected. So I'm first going to show you the piece of malware that I'm running. This is the run malware script that I'll be running in my Windows VM. What it does, it just copies it to the desktop and then changes it to .exe and then starts it, runs it. And give me a sec. I'm going to... So this is just a simple piece of ransomware. It's a PTI ransomware, and when you run it, it just... when you run it, then it will restart your computer and it will do a scan, a disk scan. Looks pretty normal at this point. I'll fast forward because it takes some time. And then you're supposed to pay some stuff by visiting this onion link. So it's a read-only VM. I'm just going to restart it. But what we're going to see is that when you drop this binary into, I'm going to shut down the VM first. When you drop this binary into the Gmail compose window, it actually tells you that it's malware. So it successfully classifies this as a piece of malware. I'm going to send it to, I'm going to try to send this to an email address that I own. And the malware binary is actually here. So when you drag and drop, you see that there's virus detected. And it doesn't actually allow you to attach it. So even it tells you there's error attaching your file, and it doesn't let you do anything. So what I'm going to do is to generate adversarial version of this malware with the model that I pre-trained. So as I mentioned earlier, it's a 4-layer feed-forward neural network with a sigmoid activation function. And what we're going to do is to just run it through this model and then generate a version of this piece of malware that is able to trick the Gmail malware classifier. And then we're going to send it into a Gmail account and open this file from the Windows VM to show that it actually went through the Gmail system. And when I download this attachment through Gmail in the Windows VM and execute it, it does the same thing. So again, the generation of these malware samples, I'll fast forward because it takes some time. Okay, Windows VM is restarting up. Okay, so it generated the samples, and it generated 5 samples here. The chance of it tricking the malware classifier is about 60%. Some of the samples will successfully be able to be attached. Some of them will not. So, for example, if I look at malware 40, it is a version that's generated with this framework, but then it doesn't successfully bypass the classifier. So that malware 20 does. So let's just go with one of them. I'm gonna rename this to something else, a little bit less suspicious looking. So I'm gonna call it definitely not malware, and then I'm gonna put it into this window, and then I'm gonna send it over. Okay, so I'm gonna sign in here. This is the Windows VM. Go to Gmail. Okay, so the email successfully sent. See that there's a .bin file. Just gonna download it. Gotta rename it to .exe. I could have run it with the same script earlier. So I'm gonna move it to the desktop first, and I'm gonna try to run it, and I realized that it's a .bin file, so I'm gonna change it to .exe. And I'm gonna run it. So again, if we see the same kind of behavior, which is the computer restarting, then we see that the malware actually retains its malicious behavior. And I'm gonna fast forward through this scan part. 59%. Yeah, so we see that this piece of malware actually traveled through the Gmail system, and then we downloaded it into a Windows VM, and it successfully infected the Windows computer. So why is this possible? A lot of this is still open research, and a lot of reasons why we can trick machine learning classifiers with such ease and with relatively low level of complexity is still an open research problem. A lot of what has been stipulated so far is because of the manifold learning problem. People have been stimulating that it's because the classification of the classification that's done within deep neural nets is too linear in the decision boundary. There are some blind spots when you are looking at when you're looking at the curves of a deep neural network, and fundamentally, there's a mismatch between what is learned in the model and what we think the model is learning. But in general, is the model just not learning anything at all? I think that's a pretty pessimistic view. There's a lot of work done in explainability that offers a lot of hope for how we can understand what a machine learning model actually learns and what it's actually doing behind the scenes. But this means that deep learning algorithms or machine learning models in general are actually pretty susceptible to manipulative attacks, whether they're causative or targeted, whether you have access to just the training phase or just the testing phase or both. You should use it with caution in critical deployments, especially since a lot of machine learning is used in critical deployments today with a very high cost function. For example, it's used in self-driving cars, and there's been articles and papers being written about how using certain images that are adversarial, you can trick a self-driving car, which are typically and most commonly implemented with deep neural net object recognition models. You can trick it to recognize a green light as a stop sign and cause it to stop unexpectedly, or the other way around. And it's being used in like cancer detection, cell detection, image recognition. So it can help. So it can actually cause the wrong detection for some kind of medical imaging. And so you can go on and on. The examples are pretty endless, especially today. So you should use it with caution, especially when you're deploying it in areas where there's a very high cost function of failure. You should always evaluate a model's adversarial resilience, not just how accurate the model is in your test set. You should look at how easily you can change or alter the prediction of this particular model that you train, and make the model more robust. So how do you make the model more robust? There's no one method that works really well. And so that's why this is still an open problem. The most effective way so far is to just train the model with these adversarial examples. So let's say in the previous capture case, we generated some examples of captures that actually trick the deep neural net solver. But then if you use these adversarial examples to train this existing model and then continue onwards and make the model more and more accurate over time, we find that the accuracy of these models actually goes up quite significantly. So another open research problem is how many times you can do this retraining and regeneration of adversarial examples before you can come to some kind of convergence, or whether there is even a convergence. And that's still an open research problem, and there's no good answer to that yet. So if you're interested to work on something like that, just feel free to approach me and we can look at it together. So there's this framework that I worked on over the last year called Pwning. It's basically something that allows you to generate adversarial examples for machine learning models, arbitrary machine learning models, and it's on GitHub. A lot of the details that I didn't go into in this talk and didn't have the bandwidth to talk about is in here, and it's pretty easy to use. I think I try to make it as easy to use as possible, but feel free to go play with it and then implement your own models in here and then try to see if you can make it more accurate and more resilient to adversarial input by training it on adversarial examples. So I think why I've been talking about this is that a lot of security implications of machine learning models are ignored. A lot of machine learning is attached to critical infrastructure and critical deployments without a good understanding of how accurate they are or how resilient they are to tampering. And I think it's necessary for the security space or even the statistics space, the machine learning space, to look at how resilient this is and how we can protect it from tampering that's unexpected. And you should always train models with adversarial examples, especially if you have a model or if you have a framework or a system that's exposed to the world. So please play with it and contribute. Some interesting stuff with deep learning and privacy I don't think I'll go into today. But again, I'll go into a final few points. Why is this important? So artificial intelligence is everywhere. It's taking over almost every aspect of technology that we're dealing with. As more critical systems rely on machine learning, there's more importance for us to look at how robust they are. People with both statistical and security skill sets, people like you guys who have been looking at systems all day, who have been looking at how to hack Unix systems, how to do static analysis, binary analysis on arbitrary binaries to find flaws in them, have to look at it from this angle, have to look at machine learning from this angle and to develop more robust systems, because if you leave it all up to data scientists and just machine learning engineers, they're going to just look at the accuracy of it. So in other words, I think you have to learn how to become irrelevant. I think it's already becoming a big space, and it's going to become bigger in the next few years. Cool. So that's all I have. Any questions?
Finished with 1 minute to spare. Thank you very much. So, questions? Hopefully there are. Excellent.
Yeah.
Yeah, since you said that one of the problems is a too linear decision boundary, does making, for instance, kernel convolution layers, do they make it better, or are they just as despicable?
Yeah, so having convolutions in neural networks does make degeneration of adversarial samples a little bit less reliable. And so, but we saw, however, that it's not a reliable way of making it more robust, because the two previous examples that we saw are both using convolutional neural networks, using a typical convolutional kernel. The first one is the CFAR10. It actually uses the AlexNet convolutional neural network. That's what TensorFlow implements. And the second one actually just uses just a feed-forward neural network that's convolutional. So we can still generate samples that reliably tricks it. So even though it's slightly less susceptible, it's still not a good defense, because there's still ways of, yeah.
Okay, maybe a follow-up. Does actually, since you added noise, does using sparse autoencoders make it better, or?
I don't think that's been looked at yet. I'm not sure if that will cause any. I'm not sure if that will help much, because if the noise that we're adding is added uniformly across the entire image. So if, let's say, we added a perturbation of value 1 across the entire image, then we're not sure exactly what features or what units are actually activated within this input function that causes the wrong prediction. Because for every image, if you add the same perturbation tensor to it, different activation paths are activated. So it's not very clear like what kinds of straightforward defenses will help. And so the most effective defense today is just a brute force approach to generate more adversarial examples and retrain, generate more, retrain. But as you can imagine, like the correct space, the correct sample space of your training data is much smaller than the total space of possible inputs that will cause a classification into one of these 10 classes. So we're not sure we're fighting a winning battle here. Yeah.
I think you have something to talk afterwards over coffee. There's another question here.
Yeah, I guess one major sort of application for this would be in biometric authentication. Have you looked at anything in this area? I mean, I imagine especially if things like facial recognition would be very susceptible.
Yeah, there's some interesting stuff in facial recognition with machine learning, and I have seen some work done, not personally. I haven't worked on it personally, but there's some interesting stuff done in not just tricking facial recognition algorithms that a particular person's face actually matches to a correct face that the model is looking for, but also in terms of privacy. When a trained machine learning model that recognizes faces can actually regenerate the training samples that are used to train this model, which is pretty scary because let's say you have a distributed model that recognizes your face and my face, and the attacker only has access to the model. He can actually generate your face from the model itself, which is an interesting thought. So, there's really a lot of work that has to be done in the security and privacy space to ensure that these are protected against, the common attacks that people look at, denial of service, or just information leakage, or just kind of malicious tampering that the security industry has to look at to ensure that the stuff that's being deployed is actually safe from all of this stuff.
Also with antivirus and malware detection, have you tried any of the commercial products besides the Google thing?
Yeah, so I have played with one vendor which I can't talk about that much, but because there isn't really a patch that you can apply onto a machine learning classifier, you can apply a patch to the machine learning you kind of apply a patch to the machine learning portion of the classifier engine to make it more accurate, reliably. What people have done is to combine machine learning with other kinds of more heuristic-based approaches in order to prevent against very obvious brute force attacks or very obvious adversarial examples. And using that, you can reliably try to find if someone is trying to bypass your system using such brute force methods. But I think it'll be an interesting project if you can get access to a lot of the machine learning classifiers out there that claim to use machine learning to classify malware. Then that'll be an interesting project to see how many of these are actually susceptible.
Thank you very much. Once again, Clarence, thanks so much for the interesting talk. Thank you.
Thanks.